Welcome to today's lecture. In the last lecture, we have seen demodulation methods of FM. First method we have seen is frequency discriminator, or it can also be named as slope detector. In that we have seen how we can easily detect or demodulate or recover the original signal from using a single slope detector or using the dual slope detector. And the second method we are seen as Foster Seeley, which is also referred as phase discriminator. In today's lecture, we are going to see PLL, phased lock loop, how we can detect or recover our original signal or message signal from the PLL, phase locked system. It is a type of negative feedback loop. Actually, it is used to track phase as well as frequency. Phase and frequency of the carrier component. PLL is used in clock recovery. Actually, PLL, it is not alone finding application in frequency demodulation, it is also finding application in clock recovery, which are all the places we are essential of having clock recovery. Coherent detection. Coherent detection means we need to use the crystal oscillator or carrier signal generator using the same frequency and same phase, that is carrier recovery. What is coherent detection? We have to recover the carrier signal which is used in the transmitter, similar to that in the receiver as well. The carrier drift we have to avoid, that is carrier drift need to be zero in coherent detection in order to avoid the distortion. The third, it is also finding application in FM demodulation. Superior to the frequency discriminator, the presence of large noise and low signal power, which is superior to frequency discriminator. The frequency discriminator we are mentioning as a slope detector, which we have seen in the last video lecture. Because in a slope detector we are having large noise as well as the signal power will be low. It is this PLL is compared to superior as compared to this frequency discriminator. The general block diagram for the phase locked loop is, see, this is our voltage controlled oscillator VCO. It is referred as voltage controlled oscillator. It is nothing but an oscillator, that is, it is providing sinusoidal oscillations. Voltage control, depending on the input voltage, the frequency will vary. Depending upon your input voltage, the frequency will be changing. Here we are having a loop filter. Loop filter is like the low pass filtered version. So this is a V of T. Consider this as our FM wave, that is demodulated FM signal. This is a general functioning block diagram of our phased locked loop. So what will this component will produce? This component will produce the phase difference between what is this phi 1 of t and then phi 2 of t. This component will, this multiplier will give the error signal. What is the difference between the input and output signal? So our main or purpose of implementing this VCO is to maintain this error signal to be zero, so that this incoming signal and output signal will be exactly in lock state, or it will in the phase and frequency will be in lock condition. That is, the phase difference in the input signal and output signal should be zero. The output, this VCO output phi 2 will have to be in order to that of phi 1 of t, so that it ensures phi e of t, that is phase error, needs to be zero. This VCO can be an sinusoidal oscillator, or it also can be a square oscillator, depending upon your input control voltage. So depending upon your input control voltage, your frequency will be changing. So these two are proportional. This input control voltage and frequency of t are proportional to each other. This output of the multiplier is referred as error signal. This loop filter is liking the low pass filtered version. Therefore, the output was 90 degree, the output of VCO is always like that of 90 degree phase shift. Magnitude will be same. Output of VCO is FC and 90 degree out of phase. When this condition will happen? Only when the input of VCO is 0. That is, we are not applying any signal to the VCO. Therefore, only with the oscillation it is producing, the output of the VCO is, that is, I am not applying any input here. I am not applying any input to VCO. The output of VCO will always equal to FC. FC is the unmodulated carrier frequency and which is 90 degree out of phase. When I apply the modulating signal to the VCO after the low pass filtered version, if at all it detects any changes, that will be going to the phi 2 of t. So, in the PLL is referred as, if any of the phase is detected and it is maintained to 0 means, then it is referred as locked condition. Low pass filter adjusts the frequency of the VCO in such a way that its frequency is equal to the incoming signal frequency and 90 degree out of phase. The purpose of low pass filter is, it gives the, if it detects any variations, it will pass to the VCO. So, depending upon your input control voltage, your frequency will be changing, and this frequency will be again using this error signal, it will be subtracted from here. It will give the changed voltage here. It maintains the, always try to maintain the, this negative loop is always trying to maintain the phase error as 0. Assume, so again we'll redraw our circuit here. This is our loop filter. This is applied as input to the VCO. So, this signal is referred as S of t, that is modulated signal. This signal is referred as phi E of t and this is your V of t. So, what is our S of t? We know that S of t is the modulated signal, AC sine 2 pi FCT plus phi of t. Phi of t is nothing but 2 pi kf integral over 0 to t m of t dt. This is the frequency modulation time domain version equation. We take this as equation number 1. We know that kf is the proportionality constant for frequency modulation or frequency sensitivity constant. AC is the unmodulated carrier amplitude. Then output of VCOs, this is your S of t. And what is the output of VCO? Output of VCO is, we are taking it as R of t. Therefore, R of t is equal to AV cos, it is having the same frequency but 90 degree out of phase, so that your sinusoidal signal become cosine signal. AV cos 2 pi FCT plus phi 2 of t. This term, whole term we are taking as phi 1 of t. This term we are taking it as phi 2 of t. Then what is our phi 2 of t? Phi 2 of t is equal to 2 pi kV. kV is the frequency sensitivity constant for VCO and integral over 0 to t V of t. This signal is V of t into dt. So, this is our phi 2 of t. What is our phi 1 of t? 2 pi kf integral over 0 to t m of t into dt. This PLL is again categorized as nonlinear equivalent model and linear equivalent model. First we will see what is nonlinear equivalent model and then we will go for what is equivalent model, linear equivalent model. This generalization or model is referred as nonlinear equivalent. From this equation 1 and 2, if VCO input is 0, we just now we have seen in the locked condition, if VCO input is 0, the output of phi 2 is also is equal to 0. That is, from here we are mentioning it as phi 1, here we are mentioning it as phi 2. If input of VCO is 0, phi 2 is also 0. Therefore, that is VCO output and incoming signal. What is our incoming signal? V of t, both are 90 degree out of phase. And VCO frequency will be equal to FC. VCO frequency, what will be the VCO frequency? It will be the free running frequency, that is FC. Therefore, the output of multiplier, what is the output of multiplier? This is the first point, this is second point, this is third point. We are first taking our input of VCO as 0, so that if my input is 0, my phi 2 of t value will also be 0. Then we are having output of VCO. Output of what will be the output? E of t. E of t is mere multiplication of Km into S of t into R of t. This term we are taking it as S of t, and this term we are taking it as R of t. Therefore, Km S of t into R of t. We are taking this as equation number 3. When we substitute equation number 1 and 2 in 3, we will get our S of t term as, that is our E of t term. What is E of t? That is the error signal. Km into AC, AV, sine, this is V, sine of 2 pi fct plus phi 1 of t, cos of 2 pi fct plus phi 2 of t. We know that this is sin A plus B and cos A plus B formula, sin A plus B into cos of A plus B, which can be, that is sin A cos B. Instead of this, we can refer to sin A cos B. Both are different terms. Therefore, this we take it as whole term as A, and this we take it as whole term as B. Therefore, we can simply supply cos A sin B formula. Therefore, 1 by 2 into sin of A plus B plus sin of A minus B. So, by substituting this trigonometric form, we will get our E of t. This term is equal to Km AC AV divided by 2. This term will become sin of 4 pi fct plus phi 1 of t plus phi 2 of t plus sin of phi 1 of t minus phi 2 of t. This E of t is passing through the loop filter. This is the low pass filtered version. Therefore, this high frequency component will get eliminated. Only this low frequency component will be passed through. This is low frequency component, this high frequency component. Since here you are having 4 pi fc, therefore only this component will be passed through. This Km is the multiplier constant. Therefore, low pass filtered version of loop filter will result in V of t is equal to, so actually your E of t is equal to Km AC AV divided by 2 sin, this phi 1 of t minus phi 2 of t can be taken as phi E of t, that is phi phase error. Phi E of t is equal to phi 1 of t minus phi 2 of t. This is, you are referring it as phase error. Therefore, the loop filter or linear time system having an impulse response of h of t. Therefore, our output V of t is equal to E of t convolution of h of t. What is our E of t? We know the convolution formula, E of tau, h of t minus tau into d tau. Therefore, in order to identify the integral over, we will just take the phi 2 of t form. What is our phi 2 of t? Phi 2 of t is equal to 2 pi kV integral over 0 to t V of t dt. Therefore, d phi 2 of t divided by dt is equal to 2 pi kV V of t. What is this V of t? V of t is E of t convolution of h of t. Therefore, 2 pi kV E of t convolution of h of t. Therefore, 2 pi kV E of t convolution of h of t is nothing but E of t, what we have just now derived, E of t is Km AC AV divided by 2 sin of phi E of t convolution of h of t. Therefore, our d phi 2 of t divided by d of t is equal to this equation, 2 pi k naught into sin of phi E of t convolution of h of t. What is this k naught? K naught is the loop gain. What is this loop gain? Kv, Km, AC, AV whole divided by 2. This term, proportionality constant term, is mentioned as loop gain. So, here we will take this as equation number 4. So, we are going to implement this equation using the block diagram. The block diagram can be drawn as, this is at phi 1 of t, we know that, which is applied to the summer here from the integrator 0 to t dt. This is phi 1 2 of t. Here you are getting phi e of t, phi 2 of t minus phi e of t, phi 2 of t, phi 1 of t minus phi 2 of t, which is passed through the sine filter. Therefore, sine of, we are just passing through sine of, therefore to acquire sine of phi e of t, which is convolved with h of t. Loop gain factor is 2 pi into k naught. Here we will get d phi e of t divided by dt. This signal is applied to the integrator. Therefore, d phi e of t will become phi 2 of t. This, after a multiplier term, this multiplier term is given by 1 by 2 pi kV. The resultant signal is our v of t. This is referred as the non-linear equivalent of PLL. We are simply implementing this expression in terms of block diagram. What is phi e of t? Phi e of t is phi 1 of t minus phi 2 of t, taking sinusoidal. Therefore, this term will get sin phi e of t, which is multiplied, convolved with h of t. Here convolution with h of t, and this d phi 2 of t divided by dt is integrated over, so that we'll here phi, this acting as a negative loop. This is our v of t controlled voltage. This is referred as the non-linear equivalent of PLL. So what will be then linear equivalent? We are going to see how we can linearize this above model. Non-linear equal sine, we have sine function in this forward path, which makes this system as non-linear. Therefore, in order to avoid this non-linearity function over here, we are going for linearized model. This is a linear equivalent. Linear equivalent model of PLL. What is our phase error? Phase error is phi e of t. When you have phi e of t of 0, PL is referred to as in locked condition. So when this is phi locked condition means phi e of t is small, we are taking this property. If phi e of t is small, sin e of t, for smaller values of e of t or theta, the value will be equal to phi e of t. This is our approximation for small values. Therefore, by using this above approximation, we have identified as phi 1 of t. This is a positive term. As applied to the summer, this is our phi 2 of t. From this 0 to t dt. So this resulting expression is phi of t, having a constant factor 1 by 2 pi k naught. This is our gain, and here it is applied to the h of t. This resultant signal is referred as d phi 2 of t divided by dt, which is given to the integrator over here, and again it is multiplied by the loop gain of 1 by 2 pi kV. This is our resultant v of t. Here we have avoided our sinusoidal function, that is non-linear function. This is referred as the equivalent linear model of PLL. V of t can also be as simplified model as kVf into kV divided by m of t. That is phi 1 of t. This is simplified linear model d by dt of 1 divided by 2 pi into kV, which will gives v of t. This is referred as simplified linear model, simplified version of linear model. This we have seen demodulation of FM signal. The first part we have seen frequency discriminator using the slope detector. The second one we have seen is the Foster-Seeley method. Foster-Seeley method. And the third one we have seen is the PLL, which is we have seen both non-linear equivalent as well as the linear model.